All right, let's work our way through the setup of a two-unit process. So this is going to be our first example of a multi-unit process. So we're going to give a labeled flowchart below of a steady state two-unit process. Each stream is going to contain two components, A and B, in different proportions. We're going to have three streams. We have flow rates and compositions not known, and we want to know the unknown flow rates and compositions of stream 1, 2, and 3. So let's take a look at our flow chart and take a look at things that are labeled. So I'm not going to worry about the 1, 2, and 3 up here. I'm going to relabel them so that this is a lot more clear for us. So now we've got two units. Something's coming into 1, something's leaving 1, something goes from 1 to 2. In between, there's what's called a mixing point, where another stream is entering a stream. So that green circle is a mixing point. We have unit 2 with an output in two different directions. So what you'll see on here is that I've labeled my streams 1 through 7. So the problem asks for stream 1, 2, and 3. So that's going to be 3, 4, and 7 for me, just to make it a little bit clearer. So stream 1 is labeled, stream 2 is labeled, stream 5 and stream 6 are labeled, but we need to figure out what's going on in 3, 4, and 7. So what you're going to notice here is that I have drawn three different boundaries on this particular system. This orange line represents the overall system. And if we look at the overall system, only 5 things cross it, even though we have 7 streams labeled. Number 1 crosses the barrier, so it gets included in the mass balance for the overall system. Stream 2, stream 5, stream 6, and stream 7 all also cross this orange barrier, but you will notice that stream 3 and stream 4 do not. So stream 3 and 4 will not be shown in a balance equation written on this orange boundary. You'll also see that I've drawn a boundary around Unit 1. Unit 1 has stream 1, stream 2, and stream 3. It does not have 4, 5, 6, or 7. So if we write balances on Unit 1, we need to only be writing balances with 1, 2, or 3. Same goes for Unit 2. This one only has 4, 6, and 7. The last boundary we can draw is this green boundary at the mixing point. And this is going to enable us to look at 3, 4, and 5. So when we draw our boundaries, we have to be very careful. We can always draw an outer boundary. We can always draw a boundary around each unit process, and either a mixing or we might see splitting points. And that's going to be important. So let's go through and let's start to write some different things and different mass balances on our systems. So the first question we have to ask ourselves is, where can we write mass balances? We can write it on each unit process 1 and 2. We can write it on the mixing point, which is streams 3, 4, and 5. And we can write it on the entire system, which is streams 1, 2, 5, 6, and 7, which is what we just went over. The next thing that we should do is we should do a degree of freedom analysis. Now, this is a newer concept, and one of the things that's going to be important with degree of freedom analysis is that we do it on each of these different boundaries. So these right here, we call these boundaries. So let's add that in here in our notes. Okay, let's do a degree of freedom analysis on the overall system. So if we look at the overall system, the only unknowns that we have are related to this stream here. They're related to the flow rate and to the composition. So I'm not going to count this one up here, X7B, as an unknown because I know it's related to 7A. So by the way that I'm writing this, this will not be a relationship for me. There's only 2 unknowns. We can then say that there are 2 species, A and B, which means that there are 2 independent balances. So 2 unknowns minus 2 species or 2 independent balances is 0 degrees of freedom. So we can solve for these 2 unknowns, 7, M7, and X7A, using the overall system balance and boundary. Using the overall system boundary, that's the better way to say it. We're going to have to write a balance on A and B as well. Let's look at Unit 1. Unit 1 has a couple unknowns, and I had to rewrite my notes here a little bit because I got a little confused. And that's always something that should be careful of, right? Is unit 1, stream 1 is fully specified, stream 2 is fully specified, but we don't know what's going on in stream 3. So stream 3 is going to have the similar unknowns. We don't know the flow rate and we don't know the composition. We know that there's 2 species, A and B. So we know that we have 2 unknowns and 2 independent equations. So we can solve for 3 using unit 1 because there's 0 degrees of freedom about unit 1 if these are our unknowns. Then we can look at unit 2 and we can say in unit 2, well, only what's in stream 4 right here is unknown. Same thing, 2 unknowns, 2 species, 0 degrees of freedom. We can find M4 by using unit 2. And then lastly, we have the mixing point. At the mixing point, we only know what's coming in for 5. So let's come down here. So we actually have 4 unknowns here, and we have 2 species, which means that if 4 unknowns minus 2 independent balances is 2 degrees of freedom, we have too many unknowns here. So the mixing point is not an ideal boundary to choose because it's too underspecified for us to be able to solve right now. So what this analysis is going to do, you'll see this note over here. This is going to help us figure out which steps or balances to do first. We know we don't want to start with the mixing point. We know we need 7, 3, and 4. So we're going to have to use the overall system boundary, unit 1 boundary, and unit 2 boundary to solve this problem. So that's going to be key in terms of defining a strategy. Next thing that we need to do, right, is use that degree of freedom analysis to tell us what order we need to solve for unknowns. So the first thing we need to do is use the overall balance to find M7 and X7A. We need to use the balances on unit 1 to determine everything in the third stream and balances on unit 2 to determine everything in the fourth stream. Last step for this particular video is we're going to write the general balance equation and simplify it. So we're going to say input minus output plus generation minus consumption equals accumulation. If we have no reactive species, nothing overall, A is not reacting, B is not reacting, then the generation equals 0, consumption equals 0. We were told it was steady state, which means accumulation equals 0, which means that input is going to equal output. And remember that we want to be careful here because just because input equals the output for the overall system doesn't mean it's the same for every species. In this particular problem, that is the case, but not every problem. So just double check and make sure that you remember that this needs to be done, this step needs to be done for every species. From here, we're going to solve and we're going to see that in the next video.